So, at this point, you might be wondering, if there's no known natural way to keep a jet locked at 90 degrees to the sun, does that mean Avi Loeb is right and 3i Atlas is some kind of alien machine? That's where the story gets tricky, not because we suddenly have proof, but because this is exactly the kind of gray area where science, speculation, and hype all start to blur together. In this last part, I want to walk through what the evidence actually lets us say, what Avi is really arguing, and how we can take the weirdness seriously without jumping straight to alien spacecraft as the default answer. Let me start with the simple timeline of what actually happened. On October 2nd, 3i Atlas passed Mars at a distance of about 29 million kilometers. In everyday terms, that sounds enormous. But for planetary astronomy, that is a very favorable alignment, close enough that a good camera in Mars orbit can resolve structure in the coma that is completely invisible from Earth. We knew about this encounter months in advance, so the Mars Reconnaissance Orbiter team had time to plan a dedicated observation campaign. Mars Reconnaissance Orbiter carries a suite of instruments, but the one that matters for this story is HiRISE, the High-Resolution Imaging Science Experiment. HiRISE is essentially a very large, very precise digital camera with a half-meter primary mirror, and it was designed to pick out objects on the Martian surface as small as a coffee table. That is an absurd level of resolving power for an orbiter around another planet. Under normal circumstances, it stares straight down at Mars, mapping dunes, ice layers, and rover tracks. For 3i Atlas, we asked it to do something it almost never does. Look away from Mars, lock onto a rapidly moving point in deep space, and follow it. That maneuver is non-trivial. From Mars's point of view, 3i Atlas was sliding across the background stars at high angular speed. To keep the comet from smearing into a streak, we had to program a custom tracking rate into the spacecraft so that HiRISE would pan across the sky at just the right speed while it exposed. At the same time, we needed accurate ephemerides for both Mars and the comet, so we knew exactly where in the sky to point and how the relative geometry was evolving during the flyby. All of that planning happened quietly over the northern summer. Navigation teams, camera specialists, and dynamicists iterating until we were confident we could catch this one opportunity. Meanwhile, from Earth, telescopes including Hubble were watching 3i Atlas from a completely different vantage point. Those early images, taken when the object was still inbound toward the sun, showed a peculiar feature: a jet apparently pointing forward, roughly toward the sun, and along the direction of motion. That was already odd, but at least plausible under exotic solar heating scenarios, because at that stage, the line to the sun and the velocity vector were almost aligned. From the Earth line of sight, everything was projected onto essentially a single plane. Any three-dimensional structure in the coma was flattened into that view. The strength of the HiRISE observations is that Mars was not sitting anywhere near that same line. By the time of the October 2nd encounter, the geometry of the system had changed substantially. 3i Atlas had passed its point of closest approach to the sun, the angle between the sun's direction and its direction of travel had opened up, and Mars occupied a vantage point that gave us a genuine side view. If you imagine the comet's path as a line, Earth was more or less looking along that line, while Mars was displaced off to the side, looking at the line from a right angle. That shift in perspective is absolutely crucial. When the raw HiRISE frames came down, they looked, frankly, underwhelming at first glance. A small fuzzy blob with a faint extension against a starry background. But once we co-registered the frames, removed cosmic rays, and stacked the exposures to boost the signal to noise, the structure of the coma became much clearer. You can't resolve the nucleus itself, it's far too small, but you can see distinct linear features emerging from the central condensation. One of them we expected, a forward-pointing jet aligned more or less along the direction of motion, consistent with what Hubble and other Earth-based instruments had been seeing projected onto their line of sight. The surprise came when we overlaid the precise sun vector for the time of the observation. We know exactly where the sun was in that frame. That geometry is dictated by celestial mechanics and the spacecraft's attitude data. When you draw that vector onto the processed HiRISE image, you immediately see that the dominant jet is not pointing along it nor directly away from it. Instead, a major collimated structure extends at close to a right angle to the sun direction. In other words, from this Mars side vantage, the comet is clearly launching material in a direction that is neither sunward nor anti-sunward. Because we are scientists, the first reaction was not "this breaks physics," but "check everything." We rechecked the spacecraft orientation, the timestamp, the ephemeris of the comet, the registration of the image, the mapping from pixel coordinates to sky coordinates. We asked whether the feature could be an artifact, a residual streak from the stacking process, an internal reflection, a cosmic ray hit that slipped through the filters. All of the usual suspects. The feature, however, persists across independent reductions and across different subsets of the data. It behaves like a real structure in the coma. So what HiRISE actually gave us, beyond any interpretation, is a clean three-dimensional constraint. From Earth alone, you can always wonder if an apparently odd jet is just an illusion of perspective, flattened into your line of sight. With the Mars view, we have a genuine stereo baseline. We see one jet roughly aligned with the direction of travel, as expected from previous images, and we see another major jet that is roughly perpendicular to the sun direction in the plane of the sky defined by the Mars vantage point. That purely geometric result is what set off the current round of debate. We are no longer arguing about a blurry feature in one projection, but about a structure whose orientation has been pinned down by a unique piece of spacecraft imaging from another world. Point. To understand why a jet that is truly perpendicular to the sun is such a big deal, we have to go back to basics and talk about what actually shapes a comet's appearance. A comet is not a fluffy ball of light. It's a small, solid nucleus made of ices and dust, usually a few kilometers across, wrapped in a temporary atmosphere called the coma. When that nucleus approaches a star, sunlight hits patches of its surface, warms them up, and the ices there don't melt in the usual sense. They sublimate, turning directly from solid to gas. That gas escapes through cracks and vents and forms narrow jets, essentially geysers in vacuum. Those jets are the engines that feed the larger coma and the long tails we see in photographs. Once the gas and dust leave the nucleus, they no longer know anything about the comet's gravity. They are much too fast and essentially free. From that point on, three things matter: the direction from the sun, the pressure of sunlight itself, and the stream of charged particles we call the solar wind. All three come from the same place, the sun. And that's why comet structures in our solar system have such a strong solar orientation. If you show a comet scientist an image with no labels, 9 times out of 10 they can tell you where the sun is in that frame just by how the tails and jets are arranged. First, take solar heating. Wherever sunlight lands on the nucleus, it preferentially activates that region. If you have a dark, volatile-rich patch facing the sun, that patch becomes a blowtorch. Gas flows out more or less along the local surface normal, but on larger scales we can say that active regions are biased toward the sunlit hemisphere. If you could freeze rotation and just light up one side of the nucleus, the jets would cluster on the day side and, averaged over time, they would tend to point roughly back toward the sun. That's why sunward jets are not mysterious by themselves. They are exactly what you expect from concentrated solar heating of a heterogeneous surface. Second, consider solar radiation pressure. Photons, particles of light, carry momentum. When they bounce off or are absorbed by a dust grain, they gently push on it. For a human, that pressure is negligible. For a micron-sized grain in vacuum, it's significant over hours and days. The result is that dust released from the coma is gradually pushed away from the sun. No matter which direction the comet is moving, the dust tail is effectively blown back into the anti-sunward direction. If the comet is inbound, the dust tail trails behind it. If it is outbound, the dust tail can actually end up in front of the nucleus along the orbit, but it still points away from the sun. When we talk about the classic white dust tail in pretty images, that's what we're seeing: radiation pressure sculpting a spray of refracted sunlight. Third, there is the solar wind, a continuous outflow of charged particles, mainly protons and electrons, streaming radially outward from the sun at hundreds of kilometers per second. Electrically charged atoms and molecules from the comet's gas can be picked up by that plasma flow and dragged away, forming a straight, often bluish ion tail. Just like the dust tail, the ion tail points almost exactly away from the sun because the solar wind is essentially radial at the comet's distance. So whether we are looking at dust or gas, the rule of thumb holds. The big-scale structures in the coma and tails are strongly sun-oriented, either toward or away. Now, jets are the roots of those tails. They originate at discrete active regions on the rotating nucleus. Because comets spin, the jets sweep through space like the water from a rotating sprinkler. If you could watch one jet in slow motion as the comet turns, the material leaving the vent at any given moment moves roughly radially outward. But as time passes, the vent's direction changes and you get a curved or spiral structure in the expanding coma. We have actually seen these spiral patterns directly in well-resolved comets when the geometry is favorable. They are beautiful confirmations of the simple picture: fixed vents on a rotating, sunlit body. With that in mind, ask what it would take to have a jet that is not roughly toward or away from the sun, but nearly perpendicular to the sun's direction, and staying that way over a large distance. First, solar heating cannot directly produce that orientation because the sun is not over there. The photons are coming from one direction. They cannot preferentially sublimate material on a face that is 90 degrees away without some sort of complex light-trapping geometry, and even then, the net flow is still biased toward the illumination direction. Second, once the material has left the nucleus, radiation pressure and solar wind try their best to bend its path into the anti-sunward direction. Over thousands of kilometers, those forces accumulate. For a collimated jet to remain pointed sideways, it has to fight that tendency the whole way. You might say, all right, maybe we are catching the jet in mid-rotation. Suppose there is a patch that was sunlit earlier, produced a jet, and then as the comet rotated, that jet source swung around to the side. We do, in fact, see rotating jets that appear sideways in some comets. The crucial point is that in those cases, the structure is not a long, straight, rigid beam. It curls, it fans out, it traces a spiral or at least a noticeable curve as new material is emitted in slightly different directions over the course of a rotation. For 3I/ATLAS, the inferred rotation period is on the order of tens of hours, not months. During the time it takes for material to travel thousands of kilometers out into the coma, the nucleus has turned significantly. You would expect the jet to paint an arc, not a ruler straight line. So when we talk about a jet in 3I/ATLAS that appears collimated and roughly perpendicular to the sun vector in the high-rise geometry, the difficulty is not that physics forbids matter from going sideways. Physics allows gas to go in any direction you like. The difficulty is that we do not have a natural, sustained driver for that direction. None of the three standard actors, heating, radiation pressure, solar wind, preferentially feed or preserve a structure oriented at 90 degrees to the sun. To get such a jet, you would need either an extremely contrived situation where the active vent, the spin axis, and the orbital motion conspire to keep one plume locked at right angles to the sun for many hours, or you would need some additional force or mechanism that is not part of our usual comet toolkit. As a conservative scientist, my instinct is always to look for the contrived but still natural explanation first. Perhaps our estimate of the rotation axis is wrong. Perhaps the jet is not as straight as it looks once you deproject it. Perhaps the local microphysics of outgassing in an irregular gravitational field can channel gas along some stable fracture. Those are all possibilities worth exploring with detailed modeling. But given what we know about how thousands of ordinary comets behave, a long, stable, perpendicular jet is not something our current, sun-dominated framework produces easily. That is why this particular feature has triggered so much discussion, not because it violates any fundamental law, but because it sits in a corner of parameter space that our familiar natural mechanisms struggle to reach. When people hear that Avi Loeb thinks 3I/ATLAS might be technological, the first reaction is usually emotional rather than scientific. Either excitement, finally, proof of aliens, or irritation. Here we go again with the clickbait. As a scientist working with this kind of data, I have to park both reactions at the door and start with a different question. What exactly are we allowed to conclude from the evidence we actually have? Let's lay out the landscape. At one end, you have the conservative mainstream interpretation. 3I/ATLAS is a natural interstellar comet with some unusual properties. That view doesn't deny that the perpendicular jet is weird or that the chemistry is skewed compared to typical solar system comets. It simply says, nature is allowed to put objects in the tails of our distributions. The first few interstellar visitors we see are very likely to be outliers, because those are exactly the ones we're most sensitive to. So the job is to squeeze the natural models as hard as possible before we start invoking technology. At the other end, you have what I'll call the engineered object hypothesis, which Avi Loeb has been publicly entertaining. In his narrative, the perpendicular collimated jet is not just a puzzle for solar heating models, it's a possible sign of active control. If you imagine a probe using directed outgassing or some other propulsion to adjust its trajectory, a sideways jet that does not line up with the sun suddenly looks less absurd. In that picture, 3I/ATLAS might be some kind of interstellar vehicle, or as he suggested in interviews, a carrier dispensing smaller sentinel probes as it flies through the solar system. Now, philosophically, there is nothing unscientific about asking whether an anomaly might be artificial. Technology is just physics arranged in a particular pattern. If you had overwhelming, repeatable evidence that something was behaving in a way natural processes genuinely cannot reproduce, then somebody built it becomes a legitimate hypothesis. We already do this in other contexts. When you look at a radio signal with precisely repeating, narrow band structure and modulation, you at least check whether it could be communication. The question is not whether we're allowed to consider that, we are, but whether the bar for doing so has been reached here. In my opinion, we are nowhere near that bar with 3I/ATLAS. The reason is simple. The current anomalies live in a messy region where our models are incomplete, our data are noisy, and our geometric reconstructions are still being refined. The perpendicular jet is a good example. Is it interesting? Absolutely. Does it sit uncomfortably in our standard sun-dominated picture? Yes. But before I tell the world that we're seeing thrust vector control from an interstellar probe, I want to be utterly sure that I've ruled out more mundane possibilities. Misestimated spin axis, unresolved curvature in the jet, projection effects we haven't fully modeled, or small-scale topography channeling gas in ways our toy models don't capture. Those are all ugly, unromantic possibilities, but history tells us they are far more common than alien engineering. This is where I part ways with Avi's public framing. He tends to collect a list of unlikely things, the jet orientation, the chemistry, the object's size, its incoming direction, and then argue that the combined improbability points toward technology. The problem is that the underlying probabilities are very hard to quantify honestly. We have a sample size of 3 interstellar objects. We do not yet know what the true distribution of interstellar comets looks like. Calling something 1 in 1,000 in that context is more storytelling than statistics. When your denominator is basically guesswork, you have to be very careful about how strongly you lean on those numbers. From the outside, this often turns into a personality contest, which is unfortunate. People either rally around Avi as the brave maverick willing to say aliens out loud, or they dismiss him as a provocateur. Neither caricature is helpful. The reality is more mundane. He's a competent astrophysicist who is deliberately pushing speculative hypotheses into the public conversation. And many of us think he's over-interpreting ambiguous data. That's a normal scientific disagreement, even if the subject matter is sensational. So what do we do with an object like 3I/ATLAS? First, we keep observing it as long as we can. The geometry will continue to change as it moves away from the sun and the planets. That gives us new vantage points. If the perpendicular jet is real and persistent, its apparent orientation should evolve in a very specific way, as the viewing angles change. If, on the other hand, it's heavily influenced by projection, later images may reveal curvature or alignment we couldn't see before. Time is an ally here. Second, we invest in detailed modeling. That means running 3-dimensional simulations of gas flow from irregular rotating nuclei under realistic solar heating and plasma conditions. It also means exploring weird but natural configurations, spin axes near special angles, complex topography that funnels gas through chasms, variable vent activity. The goal is not to force a natural solution at all costs, but to map out what is genuinely possible before we throw up our hands. If after that work the feature still refuses to fit, we have a stronger case that something is missing from our physics. Third, and this is important, we communicate honestly with the public. I actually agree with one criticism you hinted at. Official channels tend to emphasize the safe, canned phrases: interstellar visitor, valuable data, unique opportunity, and gloss over the truly puzzling bits. From a public engagement standpoint, that's a mistake, because it leaves a vacuum that more sensational voices are happy to fill. We don't need to shout alien spacecraft, to be honest. We can simply say, here is a feature we don't fully understand yet. Here are the natural explanations on the table. Here is why some people are speculating more wildly, and here's what evidence would be needed to take those ideas seriously. That level of transparency builds trust. Finally, we remember that not knowing is a legitimate scientific state. It's okay to say, based on everything we have right now, the most likely explanation is still a natural, albeit unusual comet. But there are aspects that are not yet fully explained and they're worth studying. That's not cowardice. That's exactly how progress works. Every time we meet a truly strange object, we're at risk of two symmetric errors: declaring it solved too early, or declaring it supernatural or technological too early. The narrow path in between is uncomfortable, but it's where the real learning happens. So my personal stance is this: if 3I/ATLAS turns out to be a piece of alien hardware, I will gladly eat my words and celebrate with everyone else. But the responsible thing to do right now is to treat it as an extreme test of our comet physics, not as proof we've been waiting for. The anomalies it presents are valuable precisely because they force us to sharpen our models and expand our expectations of what natural interstellar debris can look like. If, after all that work, something is still left over that truly defies nature, then we can have a serious conversation about technology. Until then, the best thing we can do is keep our telescopes open and our standards of evidence high.